I have to come up with a closed loop system. Now, when I tell electronic engineers, the Lord's gave me a revolutionary electrical generator, here's the following characteristics. It has only one moving part. It has no bearings. It has no contact brushes. I can give you single or three-phase or multi-phase power output. And if that doesn't bother you enough, I can drop in a bucket of water and never short out. So I got a lot of them squirming in their chairs, but boy, they stopped there laughing right after I talked to them.
I had a revelation, a vision, a picture in my head, a picture of this, the flux capacitor.
Flux capacitor?
It's taken me almost 30 years and my entire family fortune to realize the vision of that day. My God, has it been that long?
All right, now the Lord took to have me to come up with a non-magnetic tube, as you see here, because I want to eliminate the movement of the electromagnetic field. I'm now going to take a pickup coil and wrap it around the tube to satisfy Maxwell's Faraday's law of electrical generation. And then on this side, I'm going to put a gas accelerator here, or particle accelerator. This way, I'll just put gas accelerator. And now fill this tube up with a permanently magnetized gas. Now, the reason why the EPG electrical generator system was never in existence prior to this time is because there was no form of natural gas, magnetized gas that existed at room temperature. And as a result of that, we had to develop a way of producing the magnetized gas in such a way that we could stabilize it at room temperatures. If we could do this, then we would now solve the opposing magnetic field problem. And when I fill this up with a magnetized gas, this magnetic field now emanates around the non-magnetic tube. Now, General Abramson said to me, if you could show me how you could sustain that electromagnetic field, he says, you got the world's most efficient electrical generator. Well, General, now you're saying this in front of your technical people, not me. And the answer to that question was, I said, well, General, if this chalk was a magnetic bar, a permanent magnetic bar, the magnetic field would go from end to end, would it not? Now, General, what would happen if I would take this magnetic bar now and I extend it around to form a circle without any air gap? Which way would the magnetic field go? It would go around the ring, would it not? Like a toroidal core? And that General got right out of his chair because he realized the only energy input into the system now will be only to move the magnetic field, not to create the magnetic field. So if I would now move it in such a way that the magnetic particles would now pass through the pickup coil and I transverse the pickup coil, would I not now satisfy Maxwell's and Faraday's law of electrical generation? So am I now, question, breaking the magnetic field? No, the only thing I'm doing is I'm moving the magnetic field through this tubular structure. Therefore, do I have the opposing magnetic field problem associated with rotor electric generators?
And just looking at it, it looks like it produces a continual arc of electricity in a loop, and somehow that generates power.
Infinite power.
Do a startup sequence.
Giving it a wobble. Let's give it a strike again. So that's a short circuit. And as we lift it, that starts it up. Power.
I would now put a non-magnetic turbine wheel here, and I hook a small little, or hook an electric motor here. The question is, how much energy does it really would take to move the magnetized gas through this closed-loop circuit? It would not take very much energy. It would not take a 7 horsepower motor in order to move the magnetized gas through this pickup coil. Now, since I don't have to take a great deal of energy to do that, how big, if I hooked an electric motor to this non-magnetic turbine wheel, how big would the electric motor be?
This little screw cage.
This would be, right, the little small one. Now I could operate this electric motor by AC power, but if I didn't have AC power, could I use solar?
Yep.
Now I'm not talking about using solar cells. Banks of solar cells are going to cost you $144,000 a piece. I'm talking about 2 or 3 little solar cells that are about yay big. Okay, you ever see these little cars going around with the kids play with, you know, solar cars? All right, now if I don't have solar energy available, could I use hydraulics to move the gas? But how about
Human power.
steam power?
Steam power.
Steam power, human power?
I can use the energy generated by the coil.
How about wind power? Can I use wind power?
Yeah.
All right, now I'm not talking about the gigantic windmills like NASA have. You ever seen these popular science where they have these gigantic wind blades and all this stuff? It's going up around 320 feet high. Why do they need these gigantic blades?
You need 7 horsepower.
Yeah, you need to overcome the opposing magnetic field problem associated with it. Well, now if I don't have the opposing magnetic field problem, will my windmill be about like that?
Yep.
Could I hook it on the front of the car, and as you go down the road, the windmill
Yep.
will now move the magnetized gas, produce electrical energy, go through the voltage intensifier circuit, restrict the amp, voltage to take over to produce the hydrogen gas from running car. Can I do that?
Yep.
Am I defying any laws of physics?
No.
Okay. Now we have shown that voltage disassociates the water molecule. We show the circuitry of the voltage to restrict the amp flow and allow voltage to take over, but we need to produce a lot of electrical power. Now, most of the electrical power plants are being propelled by coal or gas or what have you. We can use the water to do this, but there's cases now where we need higher energy yields. And so the EPG system was developed for this purpose. One is I was showing you with the the magnetized gas inside the closed loop tube. We're using various methods to propel the gas. Now, in this particular case, we were talking about the electric motor driving the non-magnetic turbine wheel, which could be converted to wind power and what have you. If I wanted more power output of this generator, what would I do? Could I put another pickup coil here?
Yep.
And could I put another pickup coil here? So power output of the generator is determined by what?
The amount of coils.
Right, it's determined by number one, the strength of the magnetic field, the velocity of that magnetic field, the number of turns per coil, and the number of coils, right? So all of these, do these not comply with the power factor of electrical power generation? The only thing I've done now is I have eliminated the opposing magnetic field problem, which was the greatest problem in electrical power generation. Now I'm a little tired of the non-magnetic tube, and so in some cases I now have put in an electromagnetic pump. And I come over here with an electronic pulser, and I now want to produce an electrical generator that has no mechanical moving parts to it. Now in this analysis, if my eraser was a magnet, and I would put the magnet close to the magnetic gas, would it lock onto the gas? Right. Yes.
Yeah.
All right, now, so if I move the permanent magnet, would I now move the gas?
Yeah.
So therefore, if I now take this coil and I energize this coil to produce an electromagnetic field, and I deflect this magnetic field in a vertical direction, would I not now move the gas?
We used dysprosium nitrate some time ago to make glow-in-the-dark powder. Now, most dysprosium salts have the interesting property that they are slightly magnetic. They don't retain any magnetism afterward like a ferromagnetic substance, so this would be classified as paramagnetic. It's not very impressive, but strong enough to be attracted toward a magnet. Dysprosium is thus used for making various magnetic materials such as those found in motors, actuators, and hard drives. I think this is interesting because it's a clear crystalline substance that's magnetic, very different from the dark, opaque ferrites and metals that we're normally familiar with. Thanks for watching. In this video, we're going to demonstrate paramagnetic fluid. It's ferrofluid's weaker and less famous cousin. However, it does possess the property of being transparent, which almost all ferrofluid lacks. It's also somewhat easier to make. First, we need a paramagnetic salt. Now, I showed in a previous video that dysprosium nitrate was paramagnetic, but there is a cheaper and easier to obtain paramagnetic salt, manganese nitrate. The attraction is very weak, but it's there. Paramagnetism is a form of magnetism where substances are attracted to a magnet, but themselves cannot become magnetized. It's much weaker than ferromagnetism, but present in a greater variety of substances. This effect also works for other manganese-2 salts like manganese chloride or manganese sulfate. Transparent ferromagnetic substances do exist, but are hard to come by. Moving on, here I have a saturated solution of manganese nitrate. We can see it's ever so slightly attracted to the magnet and creeps up along glass. The effect is not nearly as strong as in ferrofluid, so to help it along we're going to try and suspend it in another non-miscible fluid. Ferrofluid uses mineral oil, but we can't use that because saturated manganese nitrate solution is too dense and still won't move very much. Even in dichloromethane, which is denser than water, it's still too dense. We need to match the density by diluting the manganese nitrate. To find the right density, we start with some dichloromethane, about 15 milliliters, and add a milliliter of water which floats. Then we add manganese nitrate solution incrementally until the whole drop can easily be pulled around with a magnet. You'll need to do some trial and error to find the right amount. And there we have it, a drop of paramagnetic fluid in a dichloromethane carrier fluid. We can clearly see it being attracted to the magnet. If you give it a hard shake, the drop breaks up into lots of tiny droplets. Applying the magnet, the droplets pull toward it and coalesce back into the larger drop. Another fun trick is to make a fluorescence. The paramagnetic fluid is clear, so we can use a drop of highlighter fluid. Once it's mixed in, we shine in ultraviolet light, and now we have a fluorescent paramagnetic fluid. Here it is again close up. Exactly what use this would be, I have no idea, but I'm sure you artists can figure something out. And there you have it, a paramagnetic fluid. Parafluid. Thanks for watching.
Now, I would not point out how to make the magnetized gas for an extremely long period of time, because when a scientist comes into my laboratory and says, if you can show me how to stabilize the magnetized gas at room temperature, you're doing something. And he's right, because this will set on an evolution like you will not believe. Now, in chemistry and linking up the atoms, we're always under a natural state in order to link up the atoms to covalent link up. Now, there are a lot of ways of doing it. Now, there's 3 atoms that exist in nature that exhibits electromagnetic fields. There are iron ions, and there are nickel ions, and there are cobalt ions. And the key to the link up was to come up with a gas lattice that would stabilize at room temperature and amplify the electromagnetic field. So one of the techniques, this is not the only technique, but this is the technique that I'll relate. But there will be an evolution now in chemistry where hundreds of millions of new chemical compounds will come about as a result of this. Under the prior state of the art, there are such atoms now in this particular case to make a magnetic gas lattice. We're going to use an iron and iron ions and argon as an example. Iron, cobalt, and nickel are atoms. Now, most they look at it as a metal substance, but Really, they're composed of the same atomic structure. They only have different number of protons and different number of electrons, right? All right, so if you get them down into the atomic structure, then they operate and function just like any other atoms do. And now, the reason why iron, as an example, or cobalt or nickel exhibits electromagnetic fields is because all of their electrons rotate in the same direction. The reason why the wood and so forth does not exhibit an electromagnetic field is because their electrons pair together and they rotate in opposite direction. Okay, and there has been examples of taking atoms and exposing on a plasma under real high temperatures and high pressures, and they would start to exhibit an electromagnetic field. But tremendous energy must go into that type of system to try to generate the magnetic field. So the key is, how do you stabilize it? Well, as we pointed out earlier, that when I took the combustible gas atoms, which we call the hydrogen gas gun, and we exposed that atom to a high voltage field, we got the ionization effect occur, right? Now in this particular case, I'm using iron and argon atoms to link up. Now, traditionally, argon is an atom that doesn't link up to anything. It's chemically inert. Why is it chemically inert? And the reason why it's chemically inert is because its second electron orbit is composed of 8 electrons.
Complete octave.
Right, and as it has its 8 complete electrons, it doesn't want to covalently link up to anything. Well, now the question is how do you look at it to accomplish the problem? Well, if that has 8 electrons, why can I not now expose the argon atom to high voltage and pluck off its electrons? Can I not do that? Huh? Can I now inject laser energy into the process that aids the process of now aiding to knock off the electrons? In other words, if I had an atomic structure this way, then the electrons would go from that orbit to K, L, M, and N orbits, and then eventually be ejected off by the voltage. Can I not do that?
Yeah.
What proves that out? How about an argon laser? Yeah. It does it? All right, so therefore, the point in the hydrogen gas gun technology, get back on this a minute, if I want to be able to covalently link up with atoms that normally do not link up, then can I not just simply pluck the outer electrons of that atom and now use it as a covalent link up? So if I pluck 4 electrons from here, from the argon atom, would it not now link up with the iron ions that also have missing electrons?
Which was not possible before.
Yes, and the reason why it wasn't possible before was the invention of the VIC circuit. The VIC unit restrict amp flow, right? Now, like a neon tube, you take a high voltage of neon tube, it produced the light, it plucked off the electrons, right? And then when it was plucking off the electrons, it allowed electrons to go back in the process to stabilize it, to go ahead and pulse again at 60 cycles to release more energy, right? All right, in the VIC unit, though, when you pluck the electrons, you're not allowing electrons to.
So today I've got 200 of these N52 neodymium iron boron rare earth magnets. They're a 1/4 inch wide and an 1/8 inch tall cylinders, but they're very strong for their size. Now, I've been playing with these and I've kind of realized that they do behave similarly to, say, molecules. It's not exactly the same, but there are some similarities. Like when I push these together, you can see a chemical reaction happened, you know. They get close enough and then they'll snap together. So it's kind of like I had some polar molecules that like to link up into chains, or this would be the crystal structure here. So you got cleavage, this plane, and this plane here. And a brittle fracture along this plane, you can see. Now if I warm it up, so this crystal, you know, the molecules here, the magnets, aren't really moving around relative to each other, so this would be at near absolute zero. But if I warmed it up, you know, give it some energy, start doing this, you can see that I wind up with something that resembles a liquid. They don't really get away from each other, and they keep trying to connect into the form, but then they get moved around and they kind of slide around past each other. Now, if I stop moving around, they kind of line up back into their crystal structure, or the, you know, lining up like this. So that'd be like a fibrous crystal structure there. So doing a gas with this would be more difficult because you know, I'd have to really shake them up to get them to come apart. But there is a way to do it, because these magnets, they don't really stick in any orientation other than one. So if they're in the wrong orientation, they'll repel. Now some molecules do that. The orientation does matter in a lot of chemical reactions. But what I can do here is use the table to like hold them into a position, and now you've got something that actually sort of resembles a gas. I want to try making something. I've got some sheets of glass and some aluminum spacers here. Let's sandwich these between two sheets of glass. That way they're not able to flip around and join together like that. These sheets of aluminum here are 1/8 inch thick, so the same thickness as these magnets. So I will have to add another piece of like paper or something to give them just a little bit more thickness so that the magnets are able to slide around without too much friction. All right. So I'm adding in the magnets, as you can see. They're repelling each other. I got these ones here in the middle. They're being levitated. I love how they bounce. So I got about half of them in. And as you can already see, the space between them down here is much smaller than it is up here. It's because the weight of all the magnets up top is pushing down and forcing these down here closer together. So it's almost like as you go up, you're increasing in elevation. If I put one in backwards, so this is kind of like adding, say, a boron atom to a bunch of fluorine gas. See? Two of them have already like reacted with it. If I jiggle it around a little bit, see, I'll get a third one to react. So now I've got a trigonal planar molecule here, which in this context is similar to boron trifluoride. And if I shake it around, you can see it acts just like any other gas molecule in there. You know, it's a little bit heavier than the others. In fact, if I work it around enough, you should see it starts to move down to the bottom. Yeah, it's a heavy gas, right? So it'll work its way down. But you'll notice it doesn't just drop straight down. There's quite a bit of force still pushing it up. So it actually takes, it's got a slight downward trend, but it's not going to just drop straight through the molecules here. That's why gases are able to mix so well. They do sort of separate, but they don't separate a lot, especially if they're shaking around a whole lot. The gas molecules are going to be fully mixed. That's why if you mix hydrogen and oxygen together, they will mix. Right? Rather than have the oxygen settle to the bottom. The oxygen will be more prevalent at the bottom, but it won't completely exclude the hydrogen. Alright, so I think I can get this back out of there. This might be... Hey, look, it actually bonded and made 4. It's kind of cool. Now, might be a little tricky. Looks like I can pull it out. There we go. Alright, so I'm just going to keep adding them in now. Let's finish off all the 200 of these. There is one problem with this model, and that's the fact that these molecules are not moving. In a gas, unless it was cooled to absolute zero, there would always be some motion. And even if it was at absolute zero. And also, if you cool the gas down that much, they would come together and stick and form a solid, or perhaps a liquid in the case of helium. Now, there is one way I could impart a little bit of motion. That's to bring a magnet nearby and just kind of flip the poles, kind of vibrate them. Yeah, in a gas, they're constantly bouncing off of each other, and on average, the effect is kind of like a repulsive effect. So this is sort of simulating that. So what I've got here is basically a simulated cylinder filled with a supercritical gas in which was really dense gas, so gravity's got a strong effect on it. So now I'm going to take a piston and let's push down on this gas. Let's see what it does. Look at that, I can compress it. Now, to give it a little bit of a vibration so that it sort of balances out. Yeah, friction's a little bit high here. But if I continue pushing down, hopefully this doesn't explode again, I can get the gas to compress. See that? It actually gets really hard to compress at this point. I'm putting a lot of pressure on there and I'm having to hold it down with my fingers here. Let's vibrate the particles again to get them all balanced out to where they should be. There you go, you see the average distance between them is now shrunk. Alright, let's let this come back up a little bit. Okay, now it's stuck. Okay, there we go. Alright, and as I vibrate it, the gas comes back up out of there. So this actually kind of shows you why the speed of sound is dependent on the velocity of the particles. You see, if they're not vibrating around, I release the pressure, they don't move, right? They don't come out to fill the gap. Until I give them a little bit of a motion, then they'll start to move.
Can you actually do that behind it?
I can try. Then they'll move to fill the space that has now been given to them. Might be easier just to kind of give them a shake here. And that is, of course, why the speed of sound depends on the temperature of the gas, not the pressure. So the vibration of the molecules that allow them to jiggle out and move into the space. It's not the pressure or the distance between them. That just stuff doesn't really matter. It does a little bit, but not a whole lot. This thing is a fun little toy. I might put a top over this.
So gas expands to fill its space, but it's not filling its entire space. What's up with that?
No, it's gravity that's holding it down. See, if I remove gravity, oh dear. Let's just see, the gas is coming out of this. I'm not holding it down tight enough. See, if I remove gravity, it does spread out. See?
Yep. Where's the bearing?
There ain't one.
Where's contact brushes? Can I now either hook this up in series or parallel arrangement, come up with any power output I so desire?
Yeah. What about the geometry of that system? Can you not refine that so that you were describing this in terms of a square?
Oh yeah, sure.
Yeah, but that's not the geometry of it in real terms.
No. Geometry in real terms, it is now going circular in spiral configuration.
Right.
Were we talking about that last night?
Acceleration, right. Acceleration.
Yeah. Now, the key to it is, for an example, if I had the electromagnetic pump here, and I now had the magnetic tube like this
It
going around.
becomes a coil.
All right, now it becomes the coil. Now, if let's take an analysis of this. Let's say that coming into this, this had a given magnetic field strength. Now, in electronics, if I would take a coil and I wrap this coil many turns, the more times I'd wrap it, the stronger the magnetic field would become, right? So if I had 1x magnetic field here, and I coiled this now, and let's say I coiled this 100 times, what's the magnetic field strength of this?
It becomes exponential.
All right, so therefore it's 100 times. All right, so I now start to wrap the coils around this circular pathway, this coil pathway, as you see here.
Coil on a coil.
Coil on a coil. Now my power output is determined by, again, the strength of the magnetic field, right? The velocity of the field. And what's my next equation? The number of wraps, right, of the coil, and the number of turns per coil.
That gives you field strength.
It gives me tremendous field strength. Okay, so here I'm using now an electromagnetic pump to produce the electrical energy. Now, when you get to EMF fields, there's a reason why this was developed this way, is because the next question is, I want to eliminate as much as possible Lenz's laws. On opposite Lenz's laws, okay? So the prior state of the art says here I have a coil, and I'm now moving the magnetic field through this coil, and I'm now moving it perpendicular to the coil. So I have tremendous opposition to moving that magnetic field, as he was pointing out, right? Well, now, can I move a magnetic field inside another magnetic field?
Yes.
And could I do it in a way that minimizes the amount of opposition?
Coherent.
Absolutely.
Coherent.
Yeah, because under this analysis, the magnetic fields are moving perpendicular, so you have opposition. But if I moved it through this way, I have a minimum amount of opposition to the movement of the field, right? So when you develop an EMF field of a coil, which way does the EMF develop?
At right angles to that.
Yeah, it develops away from the coil. That's the EMF.
So you take it with the coil now.
Yeah, so now you got a situation that,
Well, you've changed the whole role of the electronics.
well, but am I defining laws of physics?
No, you're not a cross now.
Yeah. Okay. So here is the magnetic field of the gas. That's the gas, right? And this is the EMF field. So therefore, can I not pass this magnetic field through this magnetic field and have minimum amount of opposition?
Of course.
Right? So when they say they cannot do it, it's the way that you look at it, the technology.
So we've developed technology that's produced that effect, but that
Yes.
effect need not necessarily be like that as you prove.
Yes. So therefore, I've eliminated or reduced Lenz's law down to minimum, because I'm moving this magnetic field inside another magnetic field, which gives me least amount of opposition.
You're still getting the same pickup in the coils, though.
Sure. Absolutely. So
And the axis is a 0 point.
Right.
A theoretical
the
point.
center of anything is negligible force.
Right.
There's a negligible force in the center.
Theoretical axis.
Right. So the differential is from 0 on out. And so therefore we have the ability to move the magnetized gas with very little opposition to it. Now you link this up with a water fuel cell, and a water fuel cell now is producing the electrical energy. Can I not increase that electrical output still further?
You control it.
All right, now when you move the magnetic field through that alternator, that field moves at a very slow pace, very slow. So now can we increase the speed of the magnetic field? And can we not do it in a way that we can increase power output still further? So we've taken the technology now, even to a very higher state. We have now taken it to a point of solving the problem of over-unity devices by simply now injecting laser energy input into the magnetized gas. Now what I want to do is give an analysis here. Now let's say, for an example, this is exit. All right, now I want to increase power output still further, and I'm now starting to inject laser energy into the magnetized gas. Now the key was, how can we increase the magnetic field of mass, or increase the magnetic field without increasing mass? Now if you're doing that, you can do something. Now we talked about the coil wrapping, but another classic example is if I had the magnetized gas here, it's a phenomenal effect that if I would inject laser into the process, this electron would move out to a higher orbit, would it not?
Yeah.
Now in the law of physics, I better stop. In a mechanical drive system like the electromagnetic pump system to drive the magnetized gas, I pointed out in the development of the electromagnetic pump system that will drive the magnetic gas, and all of its physical parameters in producing the electrical energy very economically. Now, the question now comes, can we produce large amounts of electrical energy by moving the magnetic field even or close to that at the speed of light? Because the magnetic field moving through a rotary electrical generator is relatively very slow. Now, the key to higher power generations was in the areas that, like on over-unity devices, as we have mentioned, is that the prior art limitation was that to increase the permanent magnetic field, you had to increase mass, which meant you had to increase the energy input in to move the mass, so that inherently became a detriment to trying to produce electrical energy. So can we not now, for example, go ahead and then amplify the electromagnetic field of the mass without increasing the mass? And what we found out was that as you inject the laser energy, and the nucleus is absorbed in the magnetized gas nucleus, then this electron now will move out to a higher orbital state. And we know that under the law of physics that when you do this, something's got to happen, right? And
Anti-gravity, yes.
yeah, yes. And one thing that takes place is that this electron, the electromagnetic field now, that holds it in its outer orbit becomes weak. And when this becomes weak, then for every action there's an equal and opposite reaction, then this electron starts to spin at a faster velocity. And under the electromagnetic theory of magnetism says that whenever a negative charged particle moves through an electric static field, B, its byproduct is electromagnetic energy. You know, there's 4 forces that affects the atoms. There's electrical force, electromagnetic, weak and strong nuclear forces. It's the electrical force that really is applied to difference of potentials that applies directly to the atomic structure of the atom, and then all the other ones are just built on top of that. So in reference to increasing the magnetic field strength, it was quite obvious that all we had to do was inject and allow laser energy to be absorbed by the atoms of the gas to now cause the electron to spin at a faster rate as it's now moving away from the nucleus. This gave us the ability to increase the magnetic field without increasing the mass. And that was the answer to over unity devices. Now, we're producing now, as we inject the laser energy into the EPG system, I've now converted the non-magnetic tube into a light guide. Light guide. Now, what that means is that I've now put in a reflective surface inside the non-magnetic tube. So now when I inject laser energy, a bolt of laser energy into this system, and let's say, for example, this is a 10-watt laser, I'm now producing this magnetic field strength, A. Now, as I do this, then this laser energy, would it not now start moving through this corridor, reflective corridor, close to around the speed of light? So as a result of this, now this laser energy is starting to move this field, this pulse field, and it starts moving and bouncing back and forth and closes this loop system and produces it at an extremely fast rate close to the speed of light. So if I want to increase more power output, in one example, as we pointed out in the prior art, I could add more coils to it, right? Mm-hmm. But now I want to increase tremendous amount of power. Let's say, for example, that I would take this non-magnetic tube, and I would take it from here to Auckland. How far away is that?
20 miles.
20 miles. And then I take the tube and loop it back here. And I wrap 1,000 turns per coil around this non-magnetic light guide. And I hook these coils in series parallel arrangement all the way to Auckland and back here. And I fill it up with a magnetized gas, and then at the one end I set a laser to it. Now if I take a laser and I strike the laser, how fast would the light energy go through the tube to back to here?
Speed of light.
And then faster than you can blink your eyes, right? Less than a nanosecond, right? All right, so now if I take a 10-watt laser and I laser and I produce this magnetic field strength, it would now move close to the speed of light to come back to here. Now, when I get back to this point right here, I now laser it again, and I strike the laser again, and now I have an intensity of the field equivalent to B size. And it now compounds itself and bounces around and gets back here again. I laser it the third time, and I produce a magnetic field 3 times in its intensity. Now imagine taking that laser, and I strike the laser 1,000 times, or let's say 1,000 times in a 10-watt laser. What would this magnetic field strength be equivalent to?
Gain exponential.
1,000 times. Yeah, so it'd be 1,000 times greater than, 1,000 times from the 10-watt laser. Okay, so I have what, a 10,000 or 100,000 watt laser equivalent of moving this gigantic magnetic field. So I'm now moving this magnetic field close to the speed of light. Now, the EMF field of the coil is only generated after the magnetic field goes through the coil of wire, right? So as that bolt of laser energy is going through the gas, then there's very little resistance of this being moved through the coil, because as it's going down that coil, it sees an open corridor with very little resistance. Is that not so? So the EMF is only built afterwards. So if I would pulse this now and set this field and pulse it and hit it at this intensity, how much electrical energy do you think I can generate?
More than you ever want.
I can generate all the electrical energy for all the major cities.
So in other words, you've done the
New
equivalent
Zealand.
of breaking the sound barrier, you grew up in the EMF barrier.
Yeah, sure.
Are you saying that the laser will carry the gas around with it?
No, no, no. The gas remains stationary, and the laser action, in other words, the atoms
and contracts.
right. And so, isn't that nice?
You streamline the thing just like a hypersonic aircraft.
Right.
It's leaving the shock waves behind it.
Right.
You've got ahead of the shock waves.
Right.
Absolutely no resistance.
Isn't that amazing?
I found him in.
Now you link this electrical power generator with the water fuel cell technology. What can you not do? The technology is only limited to the imagination for you to put it to work.
That on its own, just as is just phenomenal.
Yes, but you can't run the entire economy off of this power, because as I pointed out earlier, an electric motor cannot handle the workload of an internal combustion engine. And under the law of economics, we don't have time, for example, to change to electrical drive systems for cars. Detroit, for example, is not going to change their production line when Stan Meyer shows them how to take a $2.50 recycling tube, use the exhaust gases to adjust the burn rate of hydrogen gas to co-equal that of the fossil fuels, and run it off of water. So the law of economics dictates that this the direction will go. But the evolution of its development will continue this because, as I was mentioning to several others during our break, that the main centralized power systems have turned out to be the wrong approach in order to provide power, like in the United States, because in the inter-period of time from the time the first power plant was developed, a lot of the copper wires or the electrical transmission lines are starting to crystallize. So we're starting to have breakdowns, the Brown effect occurring, or the electrical wires are now breaking down because of the high exposure of voltage, and they're crystallizing, and we don't have the copper to go ahead and replace those transmission lines, nor do we have the monies to be able to string the transmission lines. So one of the main philosophies now in the United States is to come up with a home power generation system. So we link this to the water fuel cell, and we're going to be releasing this unit, which will be the equivalent to a half size of a hot water tank, about 18 inches in diameter, and its average power draw will be 220, 300 amp draw capacity. And link this up to the water fuel cell, then we have an unlimited power source, very economic. And the only thing I'm using here is a tube, a bunch of wires, and the gas.
exciter, what dips in there, look. Activated by a magnet instead of a solenoid. And then give it some. No X-rays, a little bit of UV though.
and this would start the actual reaction. So in fact, it's backward. It's supposed to be on the other side. When
turn
you
it upside down?
Yeah, turn it upside down. Just be careful not to drop it. Just go slowly so the mercury doesn't slam in there. Okay, okay, see that? Okay, let it go like that. You see, this is the starting electrode. And you start the arc inside, and then after that, it's a little bit like a mercury discharge lamp. And when the glue discharge start, then you could put the AC in, and the DC would come out at the end.
This unit was a battery charger, so therefore runs a lower current than the ones you've seen before.
Here we can get an overview of the complete system. This one has no exciter, instead relying on a handle for the operator to start it. The AC supply is fed through this transformer, which is then tapped for various voltages. It then passes through the bulb, with the positive being produced at the cathode and the negative coming from the neutral on the transformer. The resulting DC is then fed through the inductance coil to smooth the current flow.
Talk, yes. Talk, yes.
Welcome to our ferrofluid experiment, iron oxide as well as iron dust in Gallinstan. To mix the powders, hydrochloric acid has to be used according to literature. We use 10% strength hydrochloric acid in solution. The process is repeated until no dust is further visible in the solution. A lot of hydrochloric acid is used in this process. The process can be accelerated by shaking the bottle further. From here on, the process is a literal rinse and repeat until the solution is clear, because then you know that all the excess powder and dust has been removed and the oversaturation of the Gallinstan is no longer present. After a number of successful repetitions of rinse and repeat, you have obtained your clear liquid and your Gallinstan, which you can now test for magnetic properties. Both iron as well as iron oxide, dust, Gallinstan are produced in the same way and can now be tested. But unfortunately, we do not see a response even when applying a strong neodymium magnet to the newly formed material. In a comparison, on the right side with iron powder and on the left side with iron oxide powder, we see a beautiful reaction of the iron Gallinstan. We see that the droplet in the glass rod is moving quite beautifully, as well as in the glass when the neodymium magnet comes near to it. Here the iron powder has formed an alloy with the Gallinstan, and it can transfer its magnetic properties to the full liquid metal. In the case of the iron oxide powder, it has probably been completely washed out of the Gallinstan and is no longer contained in the liquid metal. And here once more the iron Gallinstan, which forms a beautiful Rosenzweig effect in liquid metal. Our conclusions are therefore that unfortunately iron oxide Gallinstan cannot be produced, although the materials would be cheaper and much more easier to procure.
dysprosium nitrate some time ago to make glow-in-the-dark powder. Now, most dysprosium salts have the interesting property that they are slightly magnetic. They don't retain any magnetism afterward like a ferromagnetic substance, so this would be classified as paramagnetic. It's not very impressive, but strong enough to be attracted toward a magnet. Dysprosium is thus used for making various magnetic materials such as those found in motors, actuators, and hard drives. I think this is interesting because it's a clear crystalline substance that's magnetic, very different from the dark, opaque ferrites and metals that we're normally familiar with. Thanks for In this video, we're going to demonstrate paramagnetic fluid. It's ferrofluid's weaker and less famous cousin. However, it does possess the property of being transparent, which almost all ferrofluid lacks. It's also somewhat easier to make. First, we need a paramagnetic salt. Now, I showed in a previous video that dysprosium nitrate was paramagnetic, but there is a cheaper and easier to obtain paramagnetic salt, manganese nitrate. The attraction is very weak, but it's there. Paramagnetism is a form of magnetism where substances are attracted to a magnet, but themselves cannot become magnetized. It's much weaker than ferromagnetism, but present in a greater variety of substances. This effect also works for other manganese II salts like manganese chloride or manganese sulfate. Transparent ferromagnetic substances do exist, but are hard to come by. Moving on, here I have a saturated solution of manganese nitrate. We can see it's ever so slightly attracted to the magnet and creeps up along glass. The effect is not nearly as strong as in ferrofluid, so to help it along we're going to try and suspend it in another non-miscible fluid. Ferrofluid uses mineral oil, but we can't use that because saturated manganese nitrate solution is too dense and still won't move very much. Even in dichloromethane, which is denser than water, it's still too dense. We need to match the density by diluting the manganese nitrate. To find the right density, we start with some dichloromethane, about 15 milliliters, and add a milliliter of water which floats. Then we add manganese nitrate solution incrementally until the whole drop can easily be pulled around with a magnet. You'll need to do some trial and error to find the right amount. And there we have it, a drop of paramagnetic fluid in a dichloromethane carrier fluid. We can clearly see it being attracted to the magnet. If you give it a hard shake, the drop breaks up into lots of tiny droplets. Applying the magnet, the droplets pull toward it and coalesce back into the larger drop. Another fun trick is to make a fluorescence. The paramagnetic fluid is clear, so we can use a drop of highlighter fluid. Once it's mixed in, we shine in ultraviolet light, and now we have a fluorescent paramagnetic fluid. Here it is again close up. Exactly what use this would be, I have no idea, but I'm sure you artists can figure something out. And there you have it, a paramagnetic fluid. Parafluid. Thanks for watching.
I was actually able to make some really nice ferrofluid, and it spiked even better than the commercial stuff. For my last video, I had to buy the ferrofluid to get this shot, but this time, this is the stuff that I made. With a side-by-side comparison, you can see that the spikes in mine are actually sharper and bigger. When it comes to making ferrofluid, the general idea is quite simple. It's basically just a stable suspension of a magnetic iron compound in a solvent. In practice though, it's a bit harder, and it's not as simple as just mixing these two things together. The magnetic iron compound, which is usually magnetite, has to first be specially prepared as nanoparticles and then chemically coated with something to make them stable. So the question now is, how did I do it? And well, that's kind of the point of this video. I'm going to be showing you guys exactly what I did, and the first step was to make the magnetite. To do this, I needed a source of iron 3+ and iron 2+ ions. In my last video, I used ferric chloride that I made for the iron 3+ and ferrous sulfate that I bought for the iron 2+. However, this really wasn't the best way to do it. Preparing both of them myself requires a lot of time and effort, and neither of them end up being super pure. I found that it was way easier and cheaper to just use circuit board etchant. This stuff is really easy to get, and I picked up 4 liters of it from a local store for only about $50. It's about 40% ferric chloride, aka iron 3 chloride, and I used it directly as my iron 3 plus source. To get the iron 2 plus though, I had to make it myself from the 3 plus etchant, but it was quite easy. All I had to do was reduce these 3 plus ions to 2 plus ions using steel wool. So into a beaker I poured in some of the ferric chloride, and I also dumped in some steel wool. It started reacting almost immediately, and the iron 3 was being reduced to iron 2. In doing so, 2 iron 3 ions were turning into 3 iron 2 ions, which meant that the concentration was increasing. A lot of procedures that I saw online, though, didn't take this at all into account, and they assumed that the concentration was staying the same. However, in the end, I was going to have 1.5 times more iron 2 ions than the iron 3 that I started with, and this was very important to be aware of. This is because later on, when I make the magnetite, I'm going to have to mix the iron 2 solution that I made with more iron 3, and the ratio between the two is very important. Messing this up, especially by a huge factor like 1.5, would definitely lead to poor quality magnetite and ruin the whole preparation. This process was exothermic, meaning it released heat, and because of this, the solution slowly heated up. This extra heat was actually a good thing though, because it caused the reaction to go a lot faster. Over the course of just several minutes, the dark red-orange color from the iron 3 slowly disappeared and it started turning green from all the iron 2. The basic idea here was to keep adding the wool until it pretty much stopped reacting, and then to just let it sit there for a bit. I came back about 10 minutes later, and now the green color was getting a lot more obvious. All I did was just stir it around, and then I let it sit for something like another 30 minutes. By now, it looked like the red-orange color was pretty much all gone, and it was probably getting close to being done. However, I wanted to be really sure that there was no iron 3 left, so I let it sit overnight. This was what I had in the morning, and it wasn't exactly beautiful. There was still a lot of steel wool left, but there was also this whitish-green solid that had formed, which I think was just iron 2 chloride. I'm guessing there just wasn't enough water to dissolve it all, and it started precipitating out. This was of course quite easy to fix though, and I just added some more distilled water. I mixed it around as thoroughly as I could, and then like before, I just let it sit around for a bit. It eventually separated, and I saw that I had this really nice green solution, and now the next step was to get rid of all this extra junk. I did this by just passing it all through a regular coffee filter, and I drained it directly into the bottle that I was going to store it in. When everything had filtered through, I washed the beaker, the steel wool in the filter, and the filter itself with a bunch of distilled water. When I was done doing that, I took away the funnel, and I topped everything off with more distilled water until I got to the level that I pre-marked on the bottle. This gave me a total volume of about 300 milliliters, and it let me calculate the relative concentration of this new iron 2 solution. For those that are interested, I've included all of the calculations that I did here, along with some extra details. But anyway, after this, I dropped in some iron nails. This iron 2 solution is easily oxidized back to iron 3 just by oxygen in the air. However, when these nails are added, it can reduce things back to being iron 2. At this point though, the iron 2 solution was ready, and I could now actually get things started. In my last video, I used my hot plate to stir things, but I found that it wasn't nearly fast or strong enough, especially to do it on larger scales. So I went and bought a nice overhead mixer from Amazon, which was basically just a high-tech milkshake maker. Also from eBay, I picked up a cheap Teflon-covered stir rod. Okay, so now equipment-wise I was all set up, but to actually make the magnetite, I just needed one other ingredient. This was concentrated ammonia solution, which is usually around 28%, and I picked up mine online. Now to get things started, I filled up this container with about 3 liters of distilled water, and I turned on some weak stirring. Then I added 60 ml of the iron 2 solution, followed by 75 ml of the iron 3, and I let it stir for another 10 minutes. During this time, I set up an addition funnel and I filled it with about 100 grams of the concentrated ammonia. Also, you can see here that at this point, the RPM of the mixer was at 463. When the 10 minutes were up, I increased the stirring to about 1200 and I opened the addition funnel. Almost immediately, it formed a bunch of dark solid, but the mixer quickly scattered it and it disappeared. As more was added though, it started sticking around and the whole thing eventually turned brown. This was because when the basic ammonia was added, the pH slowly increased. When it got to above around 4, it started reacting with the iron 3 ions to make brown and insoluble iron 3 hydroxide. As more ammonia was added, the iron 3 ions were all eventually converted and the pH continued to increase. When it got to around 9, it started converting the iron 2 ions to iron 2 hydroxide, but these didn't exist for very long. Almost immediately after forming, they combined with the iron 3 hydroxide to make black magnetite. Now, if all I wanted to do was make some generic magnetite, I wouldn't have needed this whole setup. I could have just directly mixed my iron 2 and iron 3, and even without stirring, dumped in the ammonia. The reason that I did it this way though, was because I needed the magnetite to form as nanoparticles. This part of the process was surprisingly finicky though, and I found that even just small changes in things like stir speed or how fast I added the base could really affect the final result. In general, I wanted to stir it as fast as I possibly could because as the stir rate increases, particle size tends to decrease. However, the faster I stirred it, the more air got mixed into the reaction, which caused more iron 2 to get oxidized to iron 3. This altered the ratio of iron 3 to iron 2, and if this wasn't accounted for, the quality of the magnetite would be affected. For magnetite, the perfect ratio between iron 3 and iron 2 is 2 to 1. What I did instead though was use a lot more iron 2, and I added it as a ratio of 1.7 to 1. This way, when it oxidized and became iron 3, it would then be able to just combine with some of the excess iron 2. This gave me a bit of a buffer zone and it allowed the reaction to be a lot more tolerant to oxygen. However, when the reaction was done, I also didn't want excess iron 2 still floating around. The speed that I added the base at also affected particle size, but this too was dependent on the stir rate. A faster addition could lead to smaller particles, however, if the stirring weren't fast enough, it could cause larger ones to form instead. So basically, if I stirred it too quickly, I might get too much oxidation, but if I stirred it too slowly, the particle size might become too big. On top of this, there were other variables, like how much extra water I had to include in this reaction, and things like temperature, and I had to find a balance between all these factors. It's definitely still far from perfect, but what I found worked was to do it at room temperature with about a 20 times dilution, a stir rate of about 1200 like I said before, and to add the base over the course of 20 minutes. Adding the base did cause the mixture to slowly thicken though, so over the course of this, I slowly increased the stirring to around 1500. So 20 minutes later, I was done adding all the ammonia, and then I let it stir for another 15 minutes. While I was waiting though, I prepared the solution that I would use to stabilize the nanoparticles. This was done using oleic acid, which I got from eBay, as well as some more of the concentrated ammonia solution. So into a beaker, I added about 15 grams of oleic acid, followed by 20 ml of water and 10 ml of the ammonia. Almost immediately, the ammonia reacted with the oleic acid to form a soap called ammonium oleate. I stirred this around until it became a nice and thick goo, and it was basically ready. When it had almost just been 15 minutes, I went back to the reaction and I filled the addition funnel with 15 grams more of the concentrated ammonia. All of this ammonia was quickly added within about a minute. And when it was done, I checked the pH and I saw that it was nice and basic, probably just below 10. I then took away the funnel and I dumped in all of the soap that I had just made. It has a tendency to get stuck inside the beaker though, so to get it all out, I had to wash it a couple times with distilled water. I then let it stir over the next 20 minutes or so, and during this time, I slowly increased the RPM up to about 1900. What was happening here was an interaction between the ammonium oleate soap molecules and the magnetite nanoparticles. The charged polar ends of the ammonium oleate were being attracted to the surface of the magnetite. This caused them to adsorb to the surface of them and to stick out their long hydrophobic tails. One of the biggest issues with magnetite nanoparticles is that they tend to want to aggregate together and to stop being nanoparticles. With the ammonium oleate on their surface, though, and with all these tails sticking out, the particles are stabilized because they're physically being blocked from coming together. On the surface, I started seeing a lot of brown stuff, which can be a bit scary because it might indicate some unwanted oxidation. I think it was mostly just soapy foam, though, that was filled with extremely small particles of magnetite. I of course could be wrong about that, and it could be because of oxidation, but I just don't think that's the case. I originally took away the funnel because as this whole thing mixed, it slowly puffed up with foam, and I didn't want it getting in the way. But now that it was almost done and it seemed to be relatively stable, I brought it back. This time though, instead of filling it with concentrated ammonia, I did it with dilute muriatic acid. This was made by just mixing 1 volume of the concentrated acid with 2 volumes of distilled water. Then once it had been about 20 minutes, I started adding the acid. Right now, this mixture was still very basic, with a lot of excess ammonia, and this was what the acid attacked first. This produced a bunch of ammonium chloride, and the pH slowly decreased. When most of the ammonia was eventually consumed, it then started attacking unreacted ammonium oleate soap, as well as the ammonium oleate that was on the surface of the magnetite. In both of these cases, it converted it back to being oily oleic acid, which was completely insoluble in water. This caused the magnetite to slowly separate out, and the goal was to bring the pH down to a bit below neutral, so around 6 to 7. For the majority of this acid addition, though, things were pretty uneventful, and it didn't look like much was happening. All I did was just check the pH every few minutes to keep track of its progress. I also occasionally refilled the funnel with more 10% acid because it needed more than I could initially fit in it. When it did get close to being done, a lot of the soap foam had disappeared and the coated magnetite particles started separating from the water. In all the procedures that I read online, none of them used acid and they instead just did it by heating. This is because around 85 or 90 C, ammonium oleate starts to break down back into ammonia and oleic acid. The high heat then drives all the ammonia out of the water, and when it's eventually all gone, the solution is around neutral. However, I tried this in my last video and with some other test runs, and I never really found that it worked. It also just pushes a lot of ammonia gas into the air, which can of course be a hazard. On top of this, heating large amounts of water like this can be a pain, and it can take a really long time. So using acid is not only easier, safer, and faster, but in my experience, it actually gave better results. This finding is partially backed up by a random paper that I found which compared temperature with the quality of the oleic acid coating. They found that it was directly related, where as you increase the temperature, the quality got worse and worse. When it did eventually get to around the neutral point, the color suddenly changed. The foam all very quickly turned white, and a lot of magnetite started separating out. This wasn't immediately evident though, because it was still stirring pretty strongly, but when I turned it off, it all quickly sank to the bottom. At this point, all the magnetite was ready, and now I just had to separate it from all the water and clean it up a bit. To do this, it was actually quite easy, and all I needed was a magnet, distilled water, and some rubbing alcohol. The first step was to get rid of all that extra water, so into a beaker, I dumped off as much as I could. Then using a magnet, I pulled out most of the particles. There were some that were still floating around, but anything that didn't get almost immediately pulled out was only weakly magnetic and I didn't want it anyway. This water was then dumped off with the help of the magnet, and I did the same thing again. On the third time, though, I was actually able to include a lot of the magnetite that was sitting at the bottom. And because of this, the separation with the magnet was a lot more interesting. The goal now is to separate all the magnetite into roughly 3 equal portions. Ideally, I would have just done it as one large batch, but the strongest magnet that I had wasn't strong enough to hold this much magnetite. What I had in the beaker at this point was probably the max that this magnet could handle. So once it had separated, I took it away, drained off the water, and I got a new beaker. Into this one, I poured in what looked like the same amount, did the same thing with the magnet, and then got a third beaker. To this last one, I added the rest, and I also washed the container with a bit of water to make sure that it got out as much as possible. When I put the magnet to it, it separated out like before, but there was a lot more here than the other ones. So once I was done and I had them all lined up like this, I tried to even it out. Now, the next step was to wash the magnetite, but because the process is the same for all 3, I'm just going to show you what I did for one of them. In general though, the process was really simple. I basically just had to add distilled water and mix it around. After doing this for a bit, and when I felt like I had broken up all the solid pieces, I put a magnet under it and I counted to about 5 seconds. The highly magnetic particles separated out really quickly, but the weaker ones needed more time. So not only did this let me clean up the magnetite and wash away reaction side products, it also helped me weed out some of the crappier particles. This water wash was done a total of 3 times, and then I moved on to washing it with isopropanol. What I did here was pretty much exactly the same, except I found that with the first couple washings with the alcohol, it always takes a bit longer for the magnetite to separate. So for these, instead of waiting about 5 seconds before dumping it off, I waited about 15 or so. By the third one though, it was a lot quicker, and the alcohol was also pretty much completely colorless. All the washing steps were now done, but I had to somehow get it all out of the beaker and into this bowl. Doing this manually though, with a spoon or something, is a huge pain. I found that the easiest and also the cleanest way was just to add some more alcohol, mix it around, and dump it into the bowl. I then separated the alcohol with a magnet and dumped it all back into the beaker. After doing this a few times, pretty much all of the magnetite was eventually transferred. With the magnet still stuck to it, I put the bowl upside down to drain away some of the alcohol. I then did the exact same washing process on the other 2 batches, and I put them here when I was done. About 10 minutes later, it looked like most of the alcohol had drained out of them, but there still was a decent amount in there. It was really important to get them completely dry though, and to do this, I used a vacuum chamber. This was the chamber that I used, and I got it from Amazon for around $100. The pump that I used was also from Amazon, and I got it a while ago when I was working on my transparent wood project. Along with this, it was also important to get some calcium chloride drying agent, and I picked some up from Home Depot. So now to the chamber, the first thing to do was to dump in a decent amount of the calcium chloride. And then on top of this, I made a small platform using styrofoam and a piece of cardboard. I put in all the bowls with the magnetite, and I also mixed them around a bit. Then I closed the chamber and I turned on the pump, but I didn't let it go to a full vacuum because sometimes this can cause things to splatter. I instead went to a certain point and then left the valve only slightly open so that the pressure would slowly decrease. By the time that it got to a full vacuum, it looked like it was behaving itself, so I fully opened the valve. After pumping on it like this for about 5 minutes, it looked like most of the alcohol was gone, and I closed the valve again. A few hours later, I repressurized the chamber, opened it up, and mixed things around. This wasn't really necessary to do, but I did find that it does help speed things up a bit. After doing that though, I put the lid back on, pulled another vacuum, and I left it overnight. Any alcohol or water that still remained just slowly evaporated, and it was continually picked up by the calcium chloride at the bottom. By the next morning it was ready, so I opened it up and I pulled everything out. At this point, it was a really dry powder, and I scraped off as much as I could from each bowl and combined it all into one. I also weighed it and found that it was a total of about 26 grams. When I first started making ferrofluids, I assumed that the magnetite at this point was going to be really oily and gross. However, it wasn't like that at all, and it was just a regular dry powder. The larger pieces looked really solid, but they were actually really easy to just break apart with my fingers and crumble them into a dust. One thing to be careful with though was that these were nanoparticles, so it was important not to breathe any of it in. But anyway, I had now successfully made the ferro part of the ferrofluid, and the next step was to add the liquid. When it comes to ferrofluids, there are oil-based ones and water-based ones, and it all depends what was used to cover the magnetite particles. And in my case, like we saw, I covered it in oily and non-polar oleic acid, so it would of course have to be an oil-based ferrofluid. For these types, the most popular solvent that people use is kerosene because it's cheap and easy to get, and it also doesn't evaporate as quickly as some of the other solvents. To make things easier, I split the batch roughly in half because I found that mixing large amounts can be a bit of a pain. For this half, I first weighed it, and it came out to be about 12 grams. I found that a good amount of kerosene to add is 85% of this mass, so I added 10.2 grams. The moment it was added, it all started dissolving, and the liquid quickly turned black. To be fully technical here though, the magnetite isn't truly dissolving, and it's just going into suspension. This is because the nanoparticles aren't soluble in the solvent, but they're small enough that they can still easily get dispersed. The oleic acid coating then helps with this by preventing the particles from coming too close together and by also allowing them to interact with the nonpolar solvent. The result of this is a stable suspension known as a colloid, where it's almost like the magnetite is being dissolved. Even after mixing it for a few minutes though, there was still quite a bit left. Sometimes it didn't really even look like much was happening, but it's just genuinely a really slow process. To speed it up, I could have just added more kerosene, but my goal here was to get it as concentrated as possible. When it eventually looked like it was pretty much all gone, I went and got one of my magnets. I found that when there was just a bit of solid left, it could really help, but also it was just a decent test to see if the fluid was even working. When I brought it close, all the liquid pulled towards it, and it formed some nice spikes, which I was happy to see. Now in terms of mixing things, the magnet helps because it pulls all the solid stuff to one spot. It also holds it there pretty tightly, and it makes it a lot easier to squish it and to crush it on the side of the bowl. I just did the same thing for another 5 or 10 minutes, moving this glass rod back and forth, and eventually it all pretty much disappeared. I was doing all this mixing over a board like this, so once it was done, I was able to test it by just putting a magnet underneath. When I did this, I was really happy with the results, because under the magnetic field, it didn't look like it was getting any more viscous or anything. In my opinion, this was one of the most important things to see, because it's what separates a proper ferrofluid from a lot of those DIY methods that are floating around online. What those make, especially the ones that just mix printer toner with an oil, are much closer to something called a magnetorheological fluid, or just an MR fluid for short. In an MR fluid, the particles are much larger, and because of that, they aren't able to stay suspended. So when they're exposed to a magnetic field, they start separating out from the solvent, and they increase the viscosity. Depending on the particle size and how well they're coated, this can sometimes cause things to partially or even completely solidify. This all isn't to say, though, that MR fluids are a complete waste of time or that they're useless, because they are interesting in their own way. While I was working on this project, I actually made them a few times by accident, but I thought that they were still pretty cool. For example, this one was a liquid, but when a magnet was brought close to it, it got a lot thicker. When the magnet was taken away, though, it almost instantly went back to being a liquid. I think this happened because some of them were small enough to stay suspended, but other ones were getting pulled out by the magnet. So what I had here was not fully an MR fluid, and it was kind of a mix with a ferrofluid. In other cases, though, when the run was a complete failure, I ended up with particles that were all way too big. So pretty much all of them were pulled out by the magnet, and the solidifying effect was much stronger. And because of all the solid content, it was still able to form spikes, but they were a lot sharper. But anyway, getting back to the ferrofluid, I find that it's a lot more fun when it's more spread out, so I poured it all into a larger dish. In my opinion, it was definitely a lot more fun like this, and I think the visuals were a lot nicer as well. The spikes kind of look like they're solid, but what's cool is that they're still completely liquid. They aren't able to hold up much of anything, so when I touched it with my glass rod, they just moved out of the way. What I thought was interesting, though, was that there was a bunch of liquid below the spikes, and this was able to hold up the rod. The magnetized fluid there was just really strongly attracted to itself, and it was surprising how strongly it repelled the rod. The fluid is only able to spike when the magnetic field passing through it is close to being vertical. So this was what happened when I put the magnet on the side, and most of the field was traveling parallel to it. It was only able to form spikes on the ends, and the middle was just a smooth blob. When I rotated the magnet, though, it gave this cool effect. What I had here was still only half the batch, so I went ahead and mixed the other part with kerosene, and I poured it all in. All of the fluid seemed to overload the magnet, though, so I decided to try it with a much larger one that I just got that morning. It seemed to be able to handle this much fluid a lot better, and the spikes were also bigger. At this point, I was pretty much done playing around with it, but I just wanted to show one last thing. I mentioned before that it didn't get more viscous under a magnetic field, but in general, it just wasn't very viscous at all. It was pretty much the same as just regular kerosene, despite being about half magnetite. From all the runs that I've done, I've noticed that the viscosity is actually something really important to look at, and every time that it's been thicker, it's been a really bad sign. Sometimes it initially works and it kind of looks like a ferrofluid, but then over the course of a day, it usually either separates or solidifies. Most of the time, those batches just end up being garbage, but sometimes they do end up being MR fluids, which, like I said, can be interesting in their own way. To measure the yield, I transferred it all to a grad cylinder, and it came out to be just above 30 mils. There was a small loss from all the stuff that stayed stuck to the dish, but in general, this was pretty much what I usually got. Now that we've seen what my fluid did, I just wanted to quickly compare it to the commercial stuff. So this here was just some of the commercial fluid that I bought, and this was what I made. The spikes in mine are significantly bigger, and in my opinion, they're also more impressive. The size of the spikes depends mostly on the concentration of the magnetite in the fluid, and I think that mine just had a lot more in it. In every run that I do, I try to saturate the kerosene, but because this process is still a bit finicky, I haven't gotten consistent results. This run just happened to be the best one that I filmed, but I did have some that I didn't record that were much higher quality. For example, in this unfilmed one, the spikes that I got were absolutely massive. Before making it, I honestly didn't even know that it was possible for ferrofluid to spike that strongly. The process that I did was almost exactly the same though, and I'm really not sure what caused the difference. However, I am working hard on figuring it out, because having a fluid like this every time would be amazing. Now going back to the nearly empty dish, I put a magnet under it again, and you can see all these little spikes forming. I think that doing this on a small amount of the fluid is a decent test to see how good it is. When the fluid is high quality, it's easily able to form small spikes, even when there's barely anything there. I like to think of the magnetite nanoparticles as little pixels, where their size will determine the smallest spike that can form, as well as their resolution. When the particles are bigger and non-uniform in size, the resolution is bad, and they form larger and uglier spikes. When they're very small and uniform though, they make these really nice and little sharp ones. Now, besides just spiking the fluid on a dish, there are some other cool things to do with it. The first thing is to add water to a vial, and then to drop in some of the fluid. Kerosene alone is much lighter than water, but with all the heavier magnetite in it, it sinks to the bottom. Also, with all the water around, the ferrofluid no longer sticks to the glass. With magnets, I can then move it around, and it makes this pretty cool little toy. Sealing the vial was also quite easy, and I just had to fill it to the max with water, and then put the cap on. Now I honestly have no idea why, but for some reason, this thing never stops being fun to play with. At this point, I've had this thing for at least a few weeks, and I still find myself playing with it all the time. As a side note, I tried doing this with a couple different commercial ferrofluids, and it never seemed to work. By just smell, I could tell that they were kerosene based, but I think they also included a bunch of additives, which messed it up. In person though, this was another bottle that I made using that other batch that spiked really well, and you can see how much cleaner it is. It's just way smoother without all those bubbles, and it also spikes a lot more strongly. I'm really not sure why this batch turned out to be a lot more bubbly, but it must have had something to do with the surfactant. The preparation for both of them though were exactly the same, so I'm not really sure why there would be such a difference.
Things have certainly changed around here. I remember when this was all farmland as far as the eye could see. Old man Peabody owned all of this. He had this crazy idea about breeding pine trees.
I'm Daniel, and this is my family team from Secure Supplies. We have preserved and rebuilt green technologies actively around the world now for over 18 years. The water fueling and gas phase change technologies are changing the way your world's power and gas industries work. Helping you access these technologies is our life mission. Click the subscribe button now to join our technology releases and updates every Monday. And consider buying a ticket to the show by pressing the link in the description. If you would like to see the secrets ahead of time, head over to our Patreon tech training releases every Friday.
Hey, keep rolling there. No, this sucker's electrical. But I need a nuclear reaction to generate the 1.21 gigawatts of electricity I need.
Merch updates are ready. If you want to look good in the H2 hot rodding scene, and if you would like to pick up some hydrogen hot rodding merch, now is your chance. Please head over to our hydrogen hot rod shop. The link is in the description. Thanks. Alternatively, you can send me an email or join me on WhatsApp chat. The details are in the description. Let me know which thing you like and what sizes you want. Network of home builders is growing very fast. Whether it's a roadster, supercar, or a yacht build, or maybe even an industrial power gas energy project. I'm here to assist and guide you. Please head over to the Consult with Dan link in the description, book a discussion for 10 to 30 minutes, and I will save you decades of study.